What we're trying to do on this worksheet is to learn how to recognize certain characteristics and features of a function and how they will manifest themselves in the derivative. So eventually in here, we're going to want to be able to go back and forth where if we see a graph of a function, we want to be able to come up with the graph of the first derivative, or if we know the graph of the first derivative, can we figure out what the graph of the function should look like. But for now, what I want you to do is to mark up your graphs as much as possible. So if you can print this out and get some highlighters and or different colored pens, I think the color helps to show that. So I'm going to kind of go through this with you and see some of these features that I'd like you to be able to try to recognize as well. And you may want to pause it and try the next one before I get to it. So for example, one thing when you look at the function, any place where you have a relative minimum or a relative maximum, so a high point or a low point, a mountaintop or a valley, that's where we're going to have a tangent that is horizontal. And the slope of a horizontal tangent is going to be 0. And so those are going to correspond to these x-intercepts in the derivative. So what I'm trying to do on the graph of the function is put in a particular color where we see these relative minimums and maximums, and then in the corresponding place on the derivative where that shows up. For example, where we see a function that is decreasing, and I'm going to try to do this with a highlighter if I can. And so if we see in this region here, where the original function is falling from left to right, that's going to correspond to a place in the derivative where it is negative, where it is below the x-axis. And here again, we see a place, part of the original graph of the original function, where the function is decreasing, and that is corresponding to this piece of the graph where it is below the x-axis. On these regions where we see the original function is increasing, we see in the derivative graph places where it is above the x-axis. Additionally, we can see that it looks like, anyway, that the degree of the original function here looks like a polynomial. And we're going to see some other graphs that are clearly not polynomials. But in the event that it's a polynomial, this looks like it is a 4th degree polynomial. And so, as we know, the derivative then is going to go down 1, and it's going to become a 3rd degree polynomial. So as many things as you can identify here, we want to mark it up as much as possible. So I'm going to go on to the next graph, and you can pause it and try to on your own and then see what we can come up together if you like. So I'm going to start by again looking for horizontal tangents, and we can see 4 of them, and we're going to look on the derivative where those are going to correspond, and they will correspond to x-intercepts, places that on the derivative graph are 0. We can see places where the original function, oops, I want to go back to highlighter. So where the original function is decreasing and our derivative graph is negative. And here's another piece where the original function is decreasing, and that corresponds to another part where this is negative. And we see again here a part where the original function is decreasing, and that's going to correspond to a place where the derivative graph is negative. Here we're going to see regions where the original function is increasing, and they correspond to places where the derivative graph is positive. So it looks like this is a, let's see, 1, 2, 3, 4 turns makes it a 5th degree polynomial, it appears here. And this derivative looks like it is a 4th degree polynomial. It has gone down 1 degree in the case of the derivative. Okay, the next one, I'm going to move it up a little bit if I can. go. Let me try that a little more. So this now is clearly not a polynomial. So we can't make the degree argument here at all. If we look closely, it looks like there might be a horizontal tangent there. So it looks like that curve is going down a little bit before it goes up. So that is going to correspond to our x-intercept in the original, in the first derivative rather. And it looks like it went down. Oh, I forgot to switch to my highlighter. So it looks like the original function decreased. It was falling from left to right a little bit, and that's going to correspond to the part on the derivative graph that's negative. And then after that horizontal tangent, it increased, which is going to correspond to where the derivative graph is going to be positive. Can't really talk about degree on this one because this is not a polynomial, so that may be about the best. I guess we could say that it's the original function is undefined for negative values, and so is the derivative graph. So you cannot somehow gain domain. You can't make the derivative be defined in places where the original function is not. So that we cannot do. Now the next one is also not going to be a polynomial. It doesn't look like there's any place where we have a relative minimum or maximum. We don't have any mountaintop or valley, and similarly we don't see any, so there's no horizontal tangents here, and we don't see any x-intercepts there. We do see that this gets really close to horizontal as it approaches apparently an asymptote, and similarly over here it looks like the graph is approaching an asymptote, so it is getting close to horizontal. And so we can also see then in the graph of the derivative that it's approaching zero. We can notice that this is increasing. Oh, I forgot. I want to get to my highlighter. It's increasing on its entire domain, and we see that the derivative is positive on its entire domain. Now, something to note here, that this is a little higher level of maybe understanding, but it looks like the original function is its steepest. It's increasing everywhere, but those horizontal tangents is increasing slowly, faster, faster. Here's where it looks like it's going to have its steepest positive slope, and that is going to, that place where we have the steepest positive slope is going to correspond to a relative maximum, a mountaintop, a highest point in the first derivative. Okay, can't talk about degree. These are not polynomials. I'm going to slide this up. I'm going to go to the next panel, I guess. And let's make it a little bit bigger if I can. And okay, so again, we're looking for horizontal tangents. Looks like we have a relative maximum in there and a relative minimum in there. They're going to correspond to our x-intercepts on the first derivative. We can see that it is where's my highlighter? So it's going to decrease on this interval, which corresponds to a place where the derivative is negative. It is increasing on these intervals, which is going to correspond to places where the derivative is positive. This original looks like it is a polynomial, and it looks like its degree is 3. And the second one also looks like a polynomial, and it looks like a parabola, which has a degree of 2. Okay, let's look at the next one. So we have lots of little mountain tops and valleys, places where we're going to get a horizontal tangent, and those are each going to correspond to an x-intercept in our derivative graph. We can see places where it is decreasing. I want to go to highlighter. We see places where the original function is decreasing, and it corresponds to places where the derivative is positive. and we have places where the original function is increasing, and those will correspond to places where the first derivative is positive. If you want to try extending it a little further even, we talked about this a little bit, it looks like there is a steepest negative slope right there, which is going to correspond to a lowest place in the derivative. This is a little bit maybe higher level thinking. So here's a steepest positive slope, which is going to correspond to a highest point in the derivative graph. Another steepest negative slope that'll correspond to another lowest point in the graph. And these look like trig functions, so you may recognize that the original one looks like it is a sine curve. So this looks like it's y equals sine x. This one looks like maybe it's a cosine curve. So that looks like maybe a relationship between the derivative, the original function, and the derivative. I'm going to slide this up a little bit. Okay. So here we don't see any highest points or lowest points. So they are not going to be any places where we can match those. We do have a vertical asymptote here, a place where the original is undefined, and that too is going to be an undefined place in the derivative. Now we can see that the original function is decreasing on this part of the graph here, and the derivative is negative on that same part of the graph, the same domain. And the original function is increasing everywhere to the left of 0, and our original function, or our derivative graph rather, is positive everywhere. Now it's kind of tough to see, we'll talk more about this down the road too, that the gap between here, I wanted to go to my pen, not the highlighter. So the distance between these gets a little wider. So the steepness as you look at the slope of those tangent lines here is going to bring this a little further away there. So if you imagine kind of like the chimney or something, the space in between the axis and the curve, each time you take a derivative when you have this vertical asymptote is going to get a little further away. So that's something we'll talk a little bit more about down the road. Some not polynomials, although you may recognize, lost you for a minute there, I bumped that with my left hand. So this looks like it is, and you're correct if you recognize that. This is y equals 1 over x squared, which we know is x to the negative 2, and its derivative, so the derivative dy dx, is going to be negative 2x to the negative 3, or otherwise known as negative 2 over x to the third, and that's what we're seeing here. So those are the actual function and derivatives of that. So the next one, we have a horizontal tangent in here. That's going to correspond to that x-intercept there. We can see the original function is decreasing to the left of to the left of the y-axis, and that means our derivative is going to be negative. It is increasing on the part of x where x is greater than 0, and our derivative graph is going to be positive above the x-axis. We can see, hopefully this looks like it's, this looks like it's some kind of parabola, maybe y equals x squared, and so its degree is 2, and the derivative, y prime, would be 2x, or at least it's going to be degree 1. It's going to have to be 1 less degree. All right, very good. I hope this was helpful, and we'll try to do more of this. Actually, we'll be doing quite a bit more of this and get to more complicated graphs even than this down the road.